I propose we start, and I would. Damien, if you are online, may I ask you to agree people coming into the waiting room, if you can?
No, I can't, Eric. Sorry,
Okay.
I don't see.
Okay, doing it then. Okay, start. So very happy to see you all here, ladies and gentlemen. Good morning or good afternoon, wherever you are. It's my indeed great pleasure to welcome you, members of SATURN Stakeholders Group, to this meeting. My name is Eric Baudin. I work for Bureau Veritas, MARIN and Offshore, and I've coordinated the stakeholder engagement and the work on the marine spatial planning within this project. As you know, SATURN, sorry, let me, sorry.
Spoiler alert, Eric.
Yeah, sorry for that. In fact, the waiting room is disappearing from the screen. Okay. Okay, and I'm back. So I have coordinated, part of the work of SATURN, the work package 6, indeed. But as you know, SATURN has addressed many different key aspects related to underwater noise, such as standardization of terminology and measurement in work package 2, impact of noise on various species of mammals, invertebrates, and fishes in work package 3, integration of the underwater noise management of large-scale areas within the marine spatial planning framework, and of course, management and communication were essential to this, the success of this project. But today we are here to present you the results from the work carried out in the work package 4 on the design solutions that could be, as per today, considered at the ship level to reduce underwater noise. You have to acknowledge that the maritime industry and policymakers have recognized the need for action to reduce underwater noise, in addition of greenhouse gases emission. While potential solutions have been identified, there are still concrete feedback lacking from experts. And that is indeed crucial to address both these environmental and operational challenges faced by the maritime industry. So today, the experts from the SATURN work package 4, the corresponding partners, will present their studies on innovative solutions to mitigate noise, while also considering their impact on cost and carbon indexes. The insights that we will discuss today are said to be valuable contribution to the work carried out at IMO, and especially the upcoming workshop in November, that we are excited to pave the way for the replication of these solutions. While my colleagues are presenting, you can prepare your question, post them in the chat, or keep them for the Q&A session that will be the last 30 minutes of this meeting. So please note that the presentations the slides will be made available. I thank you for your attention, and now I give the floor back to Johan. And meanwhile, Johan, I accept the missing one in the waiting room. So just allow me that. And I give you back. Okay.
Okay. Thank you, Eric. If you can already go to the next slide.
Yes.
Then I'm Johan Boschers. I'm senior researcher at MARIN, and I'm coordinator of work package 4 in SATURN on the technical mitigation solutions. This work package consists of 7 tasks, of which we will only address a few of one in this presentation. Task 4.1 is on the mechanism of underwater radiated noise. This research tackles 2 topics. The first topic is an experimental study in the cavitation channel of the fundamental physical mechanisms underlying propeller vortex dynamics and associated sound emissions for propellers in open water condition and in-behind condition. The second topic is a computational study of propeller sound emission of a ship in a maneuver showing that it's especially the speed loss that leads to an increase in radiated noise. Task 4.2, I'm not sure where the background noise is coming from.
Yeah, but, if you can all mute your mics, please. Thank you.
Ah, it's gone now. Okay, thank you.
Shipping record to Metas. That time these are end user. So not yet.
So let me. Sorry again.
I just assume that's the.
All.
The company in Norway.
I think it's Jackie Guo who has his mic on.
Yeah, it's muted now.
Okay. Yeah, the second task is task 4.2, and this task consists of improving and applying various computational prediction methods for the URN of propellers, with the methods varying from boundary element methods combined with semi-empirical methods to RANS and large eddy simulations. Furthermore, experimental techniques were applied to measure the reverberation of sound in the cavitation test facility and to investigate the diagnostics of propeller sound using near-field measurements. So task 4.3 to task 4.6 will be presented today. There's another task that's 4.7. It's the designated source level assessment matrix. And this task consists of experimental analysis through model tests of a URN of a thruster at oblique inflow angles and of a water jet, and a desk study to evaluate an alternative non-dimensionalization method of full-scale URN data, which is based on propeller parameters such as propeller diameter and tip speed. Most of the deliverables of this work package and the SATURN as a whole can be found on the website, which you see over there under results and resources. Today we will focus on the technical solutions. The technical solutions consist of solutions for a twin screw ferry, being a pumpjet installation, a trochoidal propulsor installation, and a propeller redesign, and solutions for a single screw tanker, which are a bubble injection below the hull to mitigate machinery noise, and bubble injection into the propeller disc in order to mitigate propeller cavitation noise. Today we will also have a presentation on the cost-benefit analysis of these technical solutions, and this gives a complete analysis of the various technical solutions by also considering the implications for the various energy efficiency indices and costs, and by considering the change in the overall radiated noise. The outline for today is presented in the next slide. We have decided, let's say, that each technical mitigation measure will be presented by the person that's most closely involved in that one. First for the twin screw ferry, then for the single screw ferry, and in addition, some of the technical mitigation measures were also analyzed in work package 6 by a noise mapping study, and 2 sheets on that will be presented by Eric. This presentation will finalize with the cost and benefit analysis, but we will start first with the presentation by Davide on the design and analysis of the pumpjet propulsor.
Yes, thank you, Johan. Good afternoon, everybody. I'm Davide Grassi from Cetena Fincantieri. I'm a naval architect in the numerical naval architecture department. I am mainly involved in propeller and hull optimization. Today I will present through a few slides the pumpjet retrofit design we made for this project. The goal of this task is to design a pumpjet that can be used as a retrofit for the existing propeller that is installed on a test case ferry ship. The idea behind is to use a system-based design optimization tool to design the shape of the different part of the pumpjet and then analyze and compare both the original propeller and the pumpjet geometry through some dedicated CFD analysis and also model test. With regard to the model test, as I will explain later, we perform all these experiments in the large cavitation channel of Sirehna in Rome, Italy. The scope of this kind of experiment was to evaluate the performance of the original blade and the pump jet, but also the wake flow, the cavitation pattern, and also the emitted noise. Through the CFD analysis, we have the chance to compare the original blade and the pump jet in full scale, whereas through the experiments, of course, we got only model test, model scale results that needed to be extrapolated to full scale. Next slide, please. So a few words regarding the design loop we apply for this case. We started from a combination of available sea trial on the existing vessel and also model test. We made some preliminary activities, like, for example, the 3D CAD modeling of the hull, of course, but also some preliminary CFD analysis, like the barrel resistance analysis that allow us to compare and to use this result as an input for the design of the pump jet. Besides this, we need to choose a layout of the pump jet, because for this propulsion tool we have many options. For example, we can go with accelerating or decelerating duct. In the first case, we can gain efficiency. In the last case, by reducing the flow field at the rotor tip, we have the chance to reduce the emitted noise. We can also choose between a rotor stator or a stator rotor. That means that the rotor is in the front part of the pump jet or in the rear part of the pump jet. We decided to go with the rotor in the forepart, so upstream of the stator, because this allows us to install more easily the pump jet on the experimental facility. We had also to decide about the number of blades. We made a lot of studies running different number of blades, and then we came to a solution where we have 7 blades for the rotor and 9 for the stator. All these studies made a kind of input, a set of input data for the design of the pump jet, like the nominal wake, the thrust, and the reference power. With regard to the design of the pump jet, as I said, we use a system-based design optimization approach, where the solver used to evaluate the different geometries for the stator and the rotor and the duct is a simplified CFD model that uses artificial wake and the frozen rotor approach. Through a genetic algorithm, we came to the optimum solution in terms of efficiency and also cavitation pattern. Then we got the final design, and as I said at the beginning, we ran some CFD full-scale analysis to evaluate the efficiency and also the cavitation pattern of this pump jet design and compare it with the original blade. Next slide, please. Here you can see some results in terms of efficiency, so in terms of propulsive performance of the original propeller on the left and for the pump jet on the right. It is possible to see the increase in efficiency we have for these two solution and also in terms of required power. For 3-speed, the lowest speed around 14 knots, medium speed that is 18 knots, and the top speed 20 knots. As it's clear here is that we got a significant increase in efficiency. For example, for the highest speed, we have an increase of 7.5%. That is really impressive. We have also to mention that for the lowest speed, the comparison is made with the original propeller running at the constant RPM with a reduced pitch. That means that in some way the efficiency of the propeller has a penalty. But we have to say that this is the way the ship owner operate this propeller. Next slide, please. If we have a look to the experiments at the Large Cavitation Channel in Rome, in terms of cavitation pattern, but also in terms of emitted noise, it's clear, as you can see here, that the cavitation pattern of the rotor, in this case, it's reduced in comparison with the original propeller. And also, if we look at the spectrum of the emitted noise at the 3 speeds we considered for the study, 14, 18, and 20 knots, it is clear that the pump jet show a reduced level of the emitted noise. In this plot, the dotted line are related to the area where the background noise of the experimental facility is above the measured noise. So in this range of frequency, is not possible to have a comparison. But in the other region, we have a reduced emitted noise spectrum, except for the high frequency at the highest speed, where we have that the red lines, that is the pump jet line, it's above the original propeller. In this region, the idea is that the cavitation coming from the rotor interfere with the stator downstream the rotor, causing this increase in noise. So we think that in a further study, it's possible maybe to optimize a little bit better in this area. Next slide, please. So to come to an outline of this study, the range of the kind of ship that on which we can apply this kind of solution are, of course, passenger vessel, but maybe also other type of ships. With regard to the effect on the emitted noise, we got a reduction up to 1510 dB, especially at medium frequencies. We have also a significant effect on the energy, on the efficiency of the propulsion system, where we have from 7 to 22% higher propulsion efficiency and from 8 to 19% reduction in power consumption. We think that the technical maturity of this device is quite high, even though we know that this studies was only focused on the hydrodynamic part and required also a mechanical study to be installed on board. With regard to the possible further studies, as I mentioned, it will be possible to improve the design of the rotor stator interference to decrease the noise emitted at high frequency and high speed. That's it from my side.
Thank you, Davide. So the floor is to Paul now.
Hi, good afternoon or good morning, everybody. So I'm Paul Muller. I'm head of hydrodynamics at Sirehna, which is a subsidiary of Naval Group in France. So I will discuss the innovative propulsion system we've been testing in SATURN, so the trochoidal propulsor. So next slide, please. So here you have an overview of the objectives. So of course, the main objective was to investigate if this kind of vertical axis propeller is a good way to reduce noise. And also a secondary objective was to make correlations, if possible, between model test results, because one part of the job was to make measurements, and computations, which were the second part of the job. For future cost effective investigation and optimizations, pretty much like David presented before. The idea is to be able to design such devices with a focus on efficiency and noise. So this kind of vertical axis propeller is, well, as it is in its name, it's a vertical axis. So you have a view on the bottom left. So the blades are vertical and are, oops, oh, no presentation anymore. So I can continue. So the blades are vertical and are rotating around the vertical axis. Each blade is rotating around its own axis, and the motor, the electric motor, is supporting the whole blades and turning around pretty much like a propeller. So when you combine the velocity of the ship and the kinematics of each blade, it produces a kind of fishtail movement. So each blade is moving like a fishtail into the flow, which is pretty much different than a classical Voigt-Schneider propulsor system, where the blades are sometimes reversed in the flow, compared to this one, where the leading edge is mostly towards the upstream flow. Next slide will be difficult to see. Eric is not there.
No, I'm there. You don't?
Oh, I cannot see the presentation, by the way. Can anybody see the presentation, or am I alone to? Okay.
No.
Is it back?
Yes, it's back. Thank you very much. This is what we did. So we started with the same reference ship as Davide presented before. And we built a model of this ship with 7.6 meter long. Well, we removed all the necessary stuff for the classical propulsion system. So the shaft line, the brackets, the rudders. I have a terrible echo. And we fitted the propeller, the vertical axis propeller below the ship. So the white part you see from the propeller system is well, the gear system is because it's fully mechanical. There is an electric motor on a single motor, and then the movement of the blades is completely controlled by gearing system. So this white box is mounted flush to the hull, and then the propellers, the blades are rotating in the water to produce this fishtail movement. So we've been testing then the model in a lake. So it's a natural environment. So we've been able to measure the noise produced by the ship and the propellers. I'm sorry, could anybody shut the mic? Yes. There is someone speaking.
Yeah, I think it's Eric, I think.
Thank you very much. Thanks a lot. So we've been testing the ship in a lake, the ship model in the lake, which is completely self-propelled, with so hydrophones placed on bottom of the lake, as seen from the picture on the bottom right, and the acquisition system was of course on shore of the lake. So we've been able to measure the radiated noise from the propeller the ship fitted with the propeller with this kind of device. So this was the first part of the job, and the second part was the numerics. So on next slide, you can see, thank you, what we've been doing. So we started with the hydrodynamics computations. So you can see on the top left corner the horizontal cut of the flow feed, so which is crossing the blades, where we can see some nice flow separations. So we've been computing the power consumed by this propeller, the efficiency of it, and then the hydroacoustics of the propeller. Plus, we've been also computing some vibroacoustics noise. So with blade vibration modes computed, plus excitation through the boundary area of the flow on the blades. So these three components of the noise are displayed on the right. So the purple line is the noise which has been measured in the lake. The blue line is the pure hydroacoustic noise, and the red and green are the vibroacoustic noise. So the main difference is that we don't take into account the cavitation in this case, and we did not expect a lot of cavitation in the model, but by the way, there was some cavitation, so the noise does not perfectly match. We still have some nice match on the blade rates, which are at the low frequency the most dominant noise phenomenon. So we have the blade rates which are good match with frequency and amplitude, which is still good news. And what we expect is that when we scale up the results, that the blades should produce on this specific design should produce roughly 5 dB more noise due to cavitation than the conventional propeller. So in this case, it's not a full success, but it's definitely due to the design, which is not improved at all. It's a very new design, so it was not on purpose designed for noise reduction. But the side news, which is very nice, is that we have a very much reduced power, necessary power, by roughly 30%. The main reason is a slight increase of the propulsion system itself and efficiency. And the second very big difference is that as we have removed the brackets, the shaft line, the rudder, so we have a lot of drag, which is reduced. And in the end, the necessary power is very much reduced compared to a conventional propeller. So, which is good news. So the idea for next is to make a better trade-off between efficiency and noise, because in this case, it was a bit more focused on efficiency than noise, this specific design. So what we expect is that this is quite relevant for twin screw vessels, because we need to have a relatively flat part of the ship to install this kind of propeller. So for single screw, it's not fully efficient or fully adapted. the effect on URN. So in this case, it's somehow close to plus 5 dBs, but we expect that with a better design, we could achieve minus 5 dB. And in this case, we have 30% gain on power consumption, which is quite large. Well, as you saw, it's still not fully mature. So we still have to make some improvement on the design, specifically for noise. So focusing on a better trade-off between efficiency and noise is the next step for this kind of propeller.
Thank you very much, Paul. You still hear me well?
Yes.
Okay, so now let me give the floor to Evertian from MARIN with regards to the work on the propeller redesign.
Yes, good afternoon, everyone. My name is Evertian Voet. I work as a researcher at MARIN, and I've been working on automated propeller design and optimization for a while. And I'd like to present the results for the optimization study where we're trying to balance the efficiency versus the underwater radiated noise properties of the propeller. Can we go to the next slide? So we have the background is that we have two goals, and we are trying to balance these two goals, meaning that you cannot minimize both. So one will impact the other. So we're going to balance these, and we use multi-objective optimization algorithms. So these are algorithms that are ideally suited to balancing various goals against each other. And then we also add a number of constraints, and one of these constraints is the low risk of cavitation erosion. So top right you see a propeller blade which has not been designed well, where the cavitation has eroded away part of the blade surface. So we definitely want to avoid this. And with a few tools. So the main tool is the propeller analysis tool called ProCal. That's what we use for day-to-day analysis. So it's an in-visit method. So no boundary layers are calculated, but you do get a very good estimate of the thrust and efficiency of the propeller and the cavitation extent within several minutes to half an hour. And then we have a workflow manager called PropArt, which is basically the geometry handling, the optimization, and the entire workflow. And we apply this to the same twin screw ferry that as for the pumpjet case. The optimizer that we use, we selected from a toolbox called Platemo. So there was one algorithm that was outperforming all the 270 other algorithms in that toolbox. They're just too many at the moment. Slide, please. So the basis is very simple. So we need a flexible geometry model for the propeller. The propeller geometry is quite simple. So here's an example of a main function top. That's, for example, the blade outline. And then we have for various parameters, you can see how this blade line would change. You can change the trailing edge of the propeller, affecting the blade area ratio or the leading edge. And we can also do this for the blade twist, the pitch, and various other properties. And then for SATURN, we also added a parametric hydrofoil function. So normally propellers are, typically designed using stock sections, NACA sections, for example, NACA 66, very popular, very good cavitation properties. But we also know that depending on the flow behind the ship and other properties, that you can tailor the sections further. So we applied a parametric model with 11 parameters per section. So the number of parameters for the propeller is quite large. I think we use 50 to 60 design variables. And then we have this custom section design. The only thing that we do need is to add a flow separation risk estimator because the code cannot handle that. So this was also added. So when we're venturing too much into areas of flow separation, then the propeller will give a penalty by the optimizer, and it will be optimized if all goes well. Slide, please. Now within SATURN, we added several source level estimation functions to estimate the overall source level of the propeller. And each of these source level estimation functions, they tie into a specific form of cavitation or a noise source. For the sheet cavitation, we have the Naval model, which is a broadband source level estimation model that responds mainly to the entire area of the cavitation under the propeller blade. So if you want to reduce it, you need to reduce the cavitating area. Then we have a tip force cavitation model developed by Johan Bossers. This model depends largely on the tip loading of the propeller. And if you want to reduce tip force cavitation noise, and this is often a dominating contribution, you need to affect the tip loading. And if you affect tip loading, you are moving away from the ID loading of the propeller, and your efficiency will suffer. Then my colleague Eric added a blade rate noise model. This also acts on the sheet cavity, but not on the area, but specifically on the dynamics. So it's a more direct method. And then we added a non-cavitating noise contribution. That is the Mitsens model. So this is basically a baseline for machinery noise of research vessels. So we added this because we thought, well, we perhaps do not need to add machinery noise models because cavitation noise is always more loud than machinery noise. But the optimizer was so aggressive in reducing the cavitation noise that then one end of the spectrum, the cavitation contribution was always lower than the machinery noise. And then it would spend too much time reducing that noise further, even though we're already quite happy. So we needed a soft landing for the optimizer. That's when we say, well, if you're below engine noise, there's no need to be less efficient. And this is why we use this Mitchell model. So nowadays we use the piano model developed by Jasco, DW Consult, and MARIN, where you can add specific machinery noise components, but the model was not available in time for the SATURN project. Now, once we have the entire source level graph, we change this to a radiated noise level. And then we weigh the overall radiated noise level by weighting groups for various mammalian hearing groups from Southall and from NOAA, for example, baleen whales up to harbor porpoises and so forth. And then we integrate everything, and then we get an overall radiated noise level for these hearing groups. And then we minimize the loudest outcome. Next slide, please. Now everything is applied in all these calculations for each propeller that we design in several design scenarios. So we analyze the controllable pitch and a fixed pitch propeller. So the ferry is fitted with a controllable pitch propeller. Then we have several design conditions. We have the ordinary, the surface speed, where it uses 2 engines and it runs at 85% power, the continuous service rating. But it can also go to its maximum speed of 20 knots, where it uses both engines. And then we also added a winter condition where the ferry speed, when there is just less demand, and then when one engine might be turned off, and we go to 85% power, which means that the controllable pitch propeller, that the pitch is reduced, and then the risk for pressure side cavitation is introduced, and that is added as a constraint. And for the fixed pitch propeller, we have comparable conditions, so we have 85% power. So that is basically the continuous service rating, 80 knots condition. And then we added 2 conditions where we added over and underloading to make sure that the design is robust. This ferry will probably not operate at these points, but this is just a common good design practice. And then we do a number of calculations. So I think we do 9 calculations per propeller. And then we do 6,000 propellers for each scenario. Slide, please. So this is the result of one of these scenarios. So this is the 4-bladed controllable pitch propeller. The original propeller also has floor blades, and this is the last generation. And when all said and done, then we get the Pareto front. So this is really the boundary in your design space, which tells you that you cannot improve your efficiency any further without giving up any of the radiated noise levels. And the black dot at left is the reference design. Well, for the same efficiency, I only win 1 dB, which was fairly, well, modest at first. We can also not make the propeller worse to reduce the noise further, because then we go to the off-design condition where there is pressure side cavitation, and we cannot combine these 2 conditions. So the low speed pressure side condition and the maximum speed condition, well, they box in your design space and you have no more room. We also analyzed the reference propeller, and then we found out that the reference propeller has, well, that's for the propeller people, there's this magenta outline that is face side cavitation. So this is an older design that suffers from face side cavitation. It is not something that you would do anymore. This propeller has been replaced meanwhile. And we also find that if you want to reduce your overall noise levels by 3 dB, you have to sacrifice about 1% of your efficiency. So that will cost you 1% of power increase. And at first we were careful and we would say, well, this only applies to this particular ferry. But this relation, 1% power for 3 dB of sound reduction, we have now found in 4 separate studies, also for a single screw container vessel and then a chemical tanker and so forth. So it's not a, well, as a rule of thumb, it's a good indication. Slide, please. Now here's the Pareto diagram where we have 4 of these scenarios in one graph. So the blue one is the same one I showed you earlier. That is for the controllable pitch with 4 blades. If you go to a 5-bladed propeller, then the optimizer is immediately able to add 1.5% of efficiency without sacrificing anything in noise. But the orange and the red dots, these are the solutions for the propeller where the section design was also varied. And we see there is a massive well, increase in your design. Well, the design space is used much better. So you can drop almost 10 dB for the same efficiency, and you can also increase your efficiency a lot more for the same noise contribution. So within your design space, adding this custom section design offers you a lot of space. So next slide, please. Now I showed you that we only had a 1 decibel increase or reduction in sound levels for the same efficiency, but that was for 20 knots. But when we look at the 80 knots condition here at right, we see that even with the NACA section, the optimizer is able to shave off 6 dB of noise for the NACA sections and a lot more for the custom section design. Unfortunately, we found out that the blade mass of the suction of these sections has more than doubled. So you would not be able to simply replace the blade and put on a new one, because then it would exceed all the manufacturing and safety tolerances of the hub. However, if for such a future design where you want to really exploit the entire design space, if you would use composite materials that have no such weight restriction, then you would be able to make a much quieter propeller with no loss of efficiency. Last slide, please. So general overview for the propeller redesign. The relevant ship types are of course all ship types, because we can apply this procedure to any type of ship, vessel and propeller type. So we do see that the effect on underwater radiated noise for the standard designs we can reduce between 3 and 9% at the cost of efficiency, though for the custom section sometimes the levels drop by 20 dB. We do see that the efficiency and underwater radiated noise are negatively correlated. So for every 3 dB you lose about 1% of your efficiency for the same type of propeller. But fortunately you can combine it with the air injection system. So this is the prairie-like system where we have injected air into the propeller disc, where we noticed that in the lower end of the frequency range that the noise levels would go down. So with such an air system you might be able to increase the cavity volume, dial up the efficiency without any negative influence on the overall noise. So technical maturity is high, so we are using these methods on a day-to-day basis. And there are of course a few outstanding actions, things that we need to improve on. So one, the optimizer is relatively quick, but not quick a lot. So we shared the optimization method with several propeller manufacturers, and they do complain that the lead time is sometimes a bit too long. So we are looking into a next generation of optimization algorithms. Now we are missing a few of the underwater radiated noise prediction tools, so that we are also working on. And for the future, we're going to couple it with high fidelity tools. Now we have an estimate when there will be flow separation, but this is just an estimate. And with a high fidelity computational fluid dynamics, you would get a direct result, and then you have to couple it. And then, of course, the other subject that is we need to couple it, the method to structural solvers, with that can analyze composite materials, so we can design for composite propellers. And this is research that's currently running at MARIN. All right, that was my final slide.
Thank you very much, Everton. Let me give the floor to Thomas Lloyd from MARIN again now.
Thank you, Erik. Good afternoon, everyone. I'm Thomas Lloyd, and I'm a senior specialist in ship noise at MARIN. And I'd like to briefly present to you our work on air injection systems for reducing underwater radiated noise. So we looked at two types of system. One is the so-called masker system, which injects an air bubble curtain around the ship hull in order to isolate the vibrating hull plating from the water, with the aim of reducing the machinery noise. And the second one is the prairie-like system, where air is injected into the propeller disc with the aim of having the air entering the cavitation and thereby dampening the collapse of the cavity of the bubbles, which is the main noise generation mechanism of the propeller. So while these two systems are designed to reduce noise, we see a clear synergy with approaches for improving energy efficiency. In the case of the masker system, you can imagine combining it with an air lubrication system, thereby achieving both a reduction in vessel resistance, in hull resistance, and machinery noise. And in the case of the prairie system, we think it could be combined with, for example, a pre-swirl device or a wake improvement device, which could be used to house the air injectors. So just covering the two air injection systems briefly, we made this ship model and tested it in our facility, our depressurized wave basin facility. The model was made to vibrate using a shaker, which you can see here on the bottom left of the slide. And we injected the air through porous hoses, which is the black strip there on the model. And the video you can see now is a high-speed recording taken from underneath the model as it sails through our tank, and you can clearly see the air bubble layer which is generated there. And for the prairie system, as I said, we used a duct to inject the air, and this was 3D printed and mounted upstream of the propeller, and the air is injected through needles which are glued into the duct. And you can see in the video there the bubbles which are flowing from the injectors towards the propeller, and then becoming entrained in the cavitation and in the tip vortex of the propeller. So we took this information from our model scale experiments, and we came up with a simplified procedure to be able to model the effect of air injection on ship source levels. So it's quite simple. We have a model for the source or the sources. So propeller cavitation and machinery noise. Then we have the air injection system performance, which we derived from the model tests, and we combine these to come up with essentially the change in source level or radiated noise level, which can be used to assess the noise performance. So in terms of the source level model, we just use simplified models. The example here shown here is the piano model, but we also came up with a procedure using the Jomopan's echo model. You can also see in the center here a graph of the spectra for the modeled air injection system performance. So the masker system is shown on the left-hand y-axis, the insertion loss, and on the right-hand y-axis is the source level attenuation due to the prairie system. And you can see that the shape of these spectra is quite different because of the differences in the systems and the way they act upon the different noise mechanisms. And then if you combine this, you come up with something like this, which is the source level spectrum for a modeled case with and without both air injection systems applied. So it's the combined effect of a reduction in machinery noise and a reduction in propeller cavitation noise. And this reduction, this delta source level, is shown here on the right-hand y-axis. And this simplified procedure has been applied in work package 6, which Erik will shortly present to you. And a script has been made available in the virtual research environment such that it can be applied by other researchers in future studies. And if you'd like more information about this, then you can find it in the references which are included in the presentation. So just to summarize about the air injection systems, for the masker system, we think it can be applied to a wide range of ship types, although you need to have a decent amount of flat bottom, particularly under the engine room. We saw reductions of up to 20 decibels in terms of underwater radiated noise, although this was focused at medium frequencies, by which I mean about 500 hertz to 2 kilohertz. We also measured a slight performance degradation when using the air injection system due to air bubbles flowing into the propeller, but we think this will be more than compensated when combined with an air lubrication system. In terms of the technical maturity, we assess it to be medium, since similar systems to this are already used on naval ships, but there's certainly room for improvement in the present application to commercial vessels. And in terms of future work, we think that it's important, of course, to test the technology on full scale, paying particular attention to the effects of vessel motions, so sailing in waves, for example, and how this will affect the bubble curtain under the ship hull. And for the Prairie system, it can be applied to most vessels, focusing on those with a screw propeller. The reduction in underwater radiated noise is up to about 10 decibels, and this is focused mainly at lower frequencies, since the system primarily reduces the characteristic hump in the underwater radiated noise in the source level spectrum for cavitation. We also measured a slight performance degradation for the Prairie system, but we think this can be removed by optimizing how the air is injected, or combining the Prairie system with a redesigned propeller, as Evert-Jan mentioned earlier. Again, maturity is medium, and full scale, as I said, for the masker system, a full scale assessment would be a logical next step. So that concludes my part of the presentation, and I'll hand over to Erik to talk to you about the work package 6 noise mapping study.
Thank you, Thomas. Thank you very much. Let me quickly give you this overview. This is the work from Quiet Oceans, namely Thomas Folego and Robert Chaban, and I have to give credit to them, even though they couldn't manage to attend today's meeting. The work performed here consists in integrating the output of some of the technical solutions that have been presented at ship level, and then to implement them at larger scale to quantify the benefit of such solution in a given area with a given ship traffic and a given time window. The three solutions that you are now familiar with a bit more, I would say, are the optimized propeller, the masker, and the Prairie systems, and the combination of those three have been simulated. In the project, 3 areas, geographical areas, have been studied, and I will illustrate with one of them, the English Channel. So you have to bear in mind that this work means that different frequencies have to be simulated. First, because as you have seen before, the solutions efficiency are frequency dependent. They are not even for all the frequencies. And of course, because the possible impacts on the fauna, because it's the main objective is to reduce the impact on the marine fauna, are also frequency dependent. So this work is simulated for different ship types, different solutions, different time windows, and so time statistic, time percentiles, and at different frequencies. So here are on the right side are given some of the results at two time window considerations, so 5% of the time and 50% of the time, so half of the time of the data time window analyzed. What we can see in English channel that is presented here is that we don't see it, but believe me, tanker and cargoes are a large part of the fleet in this area. And on the left part, these are the results for the prairie system, and we see that the prairie system mitigation have had the highest impact on source levels mitigation, and that's why this is been presented here. The mitigation effect is very strong, with 10 up to 10 dB half of the time for the combined solutions. So for the right hand side of the results, so propeller optimized plus prairie plus masker, we reach up to 10 dB. What we can distinguish as well on the graphs is that the noise mitigation extent is maximized for the highest percentiles. We know classically that the sound propagation characteristics, shallow waters, deep water condition are affecting the results, and of course also the distribution of the vessels and the vessels types. What less intuitive is that in high traffic areas, so typically where we clearly see the traffic lanes here on the top part, the masking kind of masking effect among the vessels, among the noisiest vessels and the less noisy vessels, affect the performance of mitigation, all mitigation for applied to all vessels. So it doesn't. If you see the rail area and close to the shore, you don't have the same profile of reduction. Here, for instance, we see 50% of the time. We don't have this effect that we have 5% of the time. So I won't go deep in the analysis, but just to have you kept in mind that the analysis per time percentile is essential to assess the benefit of the solution, and so after for the policymakers to consider how long a given scenario, here it's technical design scenario, but it could be operational, the approach is the same, how efficient it would be X% of the time, 5 or 50 or 100% of the time. And this is one of the key takeaways to keep in mind for this work. But the purpose is just to illustrate that from technical design solution at ship level, the next step is already mature, and it's assessing at a basin scale this technical solution. So I give back the floor to Emilio to conclude the presentation with the cost-benefit analysis of the previous solutions.
Yes, good afternoon. Thank you for joining today. My name is Emilio De Angelis. I'm in charge of Environment Signature and Monitoring Business Unit within Engineering and Research Department of Cetena, that I suppose you know is Fincantieri Research Center. Next slide, please. Today, I am presenting the cost-benefit analysis that has been performed within the work package 4 of the project, comparing different mitigation solutions that have been studied in the project, not only in terms of underwater noise, but also looking into energy efficiency and costs. Next slide. Thank you. So we start from the methodology we followed for underwater noise performance. First of all, the radiated noise level has been calculated by each partner that study each mitigation solutions. Once we define the reference operating condition, we obtained a spectrum for the baseline ship and a spectrum for the mitigated ship. Then these underwater noise data have been compared both as a spectra and as an overall value. Overall value that, as you can see in the slide, has been obtained as a logarithmic sum of the whole frequency spectrum of the spectral components. And as you can see in the slide, a difference and then being calculated. And this delta has been assumed as a reference of the improvement that has been obtained. This overall value improvement have also been calculated by applying the different weighting function that corresponds to the different sensitivity of different marine species, as shown in the second formula. If we move to the next slide, we just do a quick overview of the results for each technological solution, and then in the end we will see a full comparison among all of them. You can move through the slides. We can see different spectral behavior, but in the end we compare the overall result. Then coming to energy efficiency, we assumed as a reference the traditional and well-known indexes. That is energy efficiency design index and carbon intensity indexes. We don't go now too much into details. You can see both of them express a ratio between the amount of CO2 that is emitted into the atmosphere and the so-called transport work, so the ship capacity multiplied by the distance then the ship sails. Also here we have a quick overview. We can see good results from the energy point of view for all the solutions studied. So we can move on the next slide. Here in propeller optimization, we can see we declare that the energy efficiency is unchanged, but this was an assumption in the optimization process that has been very well described before. So I think we can move to the cost part of our analysis. It seems some word is missing in this slide. Oh, sorry, I don't see the presentation anymore. Okay, sorry, I'm back. Okay, so concerning the cost, we started from a rough estimation of the shipbuilding cost, and we performed an estimation of the delta cost necessary for the implementation of each mitigation solution. Then we also estimated the life cycle cost, both for the baseline ship and per the mitigated ship. In this life cycle cost, we took into account not only the start investment and operating traditional operating costs, but also a quantification of external costs due to each pollutant that is emitted into the atmosphere. So as a KPI for each mitigation solution, in the end we calculated CAPEX, life cycle cost, and the net present value of the life cycle cost, that is the life cycle cost discounted to now. The last thing that it's important to point out is that revenues have not been taken into account in the life cycle cost analysis, since we consider the revenues as invariant with respect to the mitigation solution. We note that this is not completely true, because, for instance, a ship that is better performing from the point of view of noise can assess different area, can have discounts on port fee and so on, but we didn't take into account that in this evaluation. So moving to the next slide, here you can see, also in this case, we don't go too much into the details. We can see something very similar for each solution. That is an increase in capex, but a decrease in life cycle cost and discounted life cycle cost. That means that it's possible to have a payback of the investment cost within the life of the ship. So in this last slide, we have a comparison among all the different mitigation solutions. And we can see what I briefly described before in the previous slide. So we can see an improvement from the energy efficiency point of view between 3 and 6%, let me say. The only exception is propeller optimization, but as we have seen before in the presentation, we assumed that for this comparison to maintain efficiency invariant for the propeller that has been optimized. From the point of view of radiated noise level, also we can see improvement for all the mitigation solution we compared. Something different for vertical axis propeller. Here in this slide summarizing, we put the worst performance, but as Paul has explained before, there is still some optimization to be done, and we can foresee better results also for the vertical propeller. And from the point of view of costs, here we point out the life cycle costs. As I said before, there is always the possibility to obtain a payback of the investment within the life of the ship. Also in this case, there is an exception related to propeller optimization, since we assumed that there were no improvement in efficiency. So obviously there is no possibility to have a payback. In the last row, we show the technical maturity of the solution from the point of view of underwater noise. Let me say that all the study solution have a high technology readiness level in a traditional sense, so they are already installed and operating on board ships. What we point out here is how much in details the optimization of them from the point of view of underwater noise has already been developed. So in conclusion, we can see we can say that in fact we didn't identify a best solution at all, but all the solutions that we studied are, however, promising. A good result is that it's possible to design mitigation solution that combine underwater noise reduction and energy efficiency improvement. Of course, it depends the reference we assume. If we start the process of optimization or refitting of a ship from a solution that has already a very good optimization from the point of view of efficiency, this is not always true, but there is a very good space of improvement usually. As I say, the payback of investment cost is almost always possible within operating life. And of course, there is no best solution, but some of them are better for retrofit, some for new build. It depends on the ship condition, of the operating profile, and so on. So I think we can give back the floor to Eric.
Yes, thank you, Emilio. Thank you all. Let me come back with the image and the phone with my phone, the sound with my phone. So now the floor is yours for questions from these presentations. So either you, yeah, Chris, welcome, and thank you for your first question.
Okay. Oh, thanks, Eric. Can you hear me okay?
Yes.
Thanks to all the presenters for the excellent work. Oh, it's absolutely fascinating. I've got a question on the last slide. The very good table. Is it possible to bring that up? That's it, yeah. So the overall life cycle costs, I guess there must have been an assumption on the price of fuel. But of course, at IMO, the greenhouse gas pricing mechanism, that's still to be determined probably in October. So could I ask what assumptions were made on the price of fuel through the life of the ship? Did you assume an increasing cost because of the progressive nature of the greenhouse gas regulations? And if so, what was that annual increase? Thanks, Eric.
Thank you.
Yes, if I'm not wrong, we assumed a slightly increase in the price of fuel in the next years. At the moment, I am not sure on the quantification of this increase, but of course I can check and we can share this information.
I'd be grateful for that. I mean, I think that could potentially make a big difference, couldn't it? You know, if we're looking at steep increases in the price of fuel, that could have a significant impact on the economics in the table. You know, it'd make it potentially much more beneficial to the ship owner to adopt some of these technologies. Thank you. It's really interesting. Thank you.
Thank you, Chris, for your good remark. And together with the next months, let's say, all these solutions being more broadly adopted will also cut down the cost of this solution, as far as any innovative solution is at the beginning of its implementation. The cost is of course high, and the more is produced, the best. Normally, the cost is dropping down as well. So all in all, it will be much more engaging for our ship owners. Any other question from the floor? I check in the chat. Yeah, Youssef, if you yeah, can take the mic, if you don't mind.
Yeah, I can explain the question if that's easier.
Yes, thank you.
Yeah, it's just so that like I put there, the updated IMO guidelines on underwater noise says, you know, we shouldn't reduce noise at the expense of GHG, and certainly like this work and, you know, other work that's been done that I've seen is said, you know, basically you can have a quiet propeller, but it comes an efficiency cost, right? And you would increase your GHG, and so it seems like one contravenes the other, unfortunately. And I know, you know, there's been some discussion there on air lubrication, but my concern is then that we, you know, it's like, well, here's a solution, but you need this add-on to mitigate the negative effect of that solution, and we're just sort of continually adding cost. And I know, you know, there's some interesting comments there with regards to, for example, EEXI. I'll tell you, as you know, I work for Canada Steamship Lines. We were currently looking to build 2 new ships. They're going to be copy-paste of old ships. Same trade, we're same dimensionally constraint, but now we're in 2025, so it's EEXI phase 3. And the shipyard said, well, simply then the ship's going to go slower, right? If you don't want to spend all this money on all these other fancy technologies, well, you know, your 14-knot ship is now a 12.5-knot ship. And so I'm going to put it, I just kind of want to make the comment, I guess, the technology and the science behind this is fantastic, and I'm actually very supportive of it. I just want to bring the ship owner's perspective on it, is that we probably end up just looking to go slower through these areas, right, as a means to mitigate noise, because the prices I've had for propellers, you know, about $500,000 for my size of ship, and the air lubrication retrofit that I got quoted for my size of ship was about €1 million, right? So that's a cost I can't pass to a customer right now because there's not a regulation, and it's too much for, I think, a ship owner to just absorb. But I do remain very supportive of all this. It's more about, let me tell you the problem, because we have to overcome it to make the ocean quieter, right? I firmly support making the ocean quieter.
Yeah, I can only receive thanks your comments. The other thing is that you represent some ship types, and for other ship types, it's might be a different story, might have less room in changing the operating profiles. We all know the story of slow steaming, where hundreds of container vessels were delivered, and then a few years after, back to the dry dock to change the bulbous bow and the propeller. I would say today there is no solution fit for all for underwater noise. There is no, and we know that for decarbonization. The very important takeaway from this work is to say we are ready to work on the trade-offs. So for the propeller, Evertian has showed clearly the efficiency in terms of noise reduction, together with keeping the same propulsion efficiency. It's a trade-off, but we can reach 5 dB, 7 dB without impairing the efficiency. They are ahead of us. There are new geometries that are much more promising, and new materials to be used are also a very interesting open door. And then the idea is to concentrate the investment cost into a dual consideration of the problem, and stop separating this problem by saying, okay, I have on my shoulders as a ship owner all the decarbonization regulation, and then I will see later on. And that's this later on that can be really detrimental for your investment and for your payback, because you can do something at the earlier stage and without any significant additional cost, and have this trade-off solved, and do your action even though there is no mandatory requirement. And then in the future, you will see if you can afford, you will still have the choice in affording with the current situation, with the current price of the carbon and on the fuel, and with the current cost of implementing a new solution, if it's worth implementing that solution or reducing speed. But many, I would say many of the ship owners I'm discussing with are more against ship speed reduction, as far as they don't decide when and where they operate. But ship reduction related regulation, to me, from what I observe, is not appears the simplest, but is not the preferred one. But CSL might have different views, but thank you for this complete, I would say, complete comment and clear explanation of the current situation from a ship owner point of view. I know we have other ship owners, without naming them, in the room. If you have more to say from different view angles, from different market sector, it would be much appreciated.
There's also another raised hand, Eric. So.
Okay, I don't see it. Okay, Alison.
Yeah.
Okay, thank you.
Hi, Eric.
No,
Yeah,
thanks.
Alison first, and then Christian, if you don't mind.
I was just going to comment on the conversation that you guys were kind of having, and to say that we at the Maritime Administration in the US have been talking to our designers and our shipyards and trying to move from the space where we are looking at the application of a single technology towards the space of the application and modeling of multiple technologies. So to the point where, you do one thing and there's this trade-off, but if you pair it with, 2 or 3 technologies that are applied to different parts of the propulsion system, or perhaps the machinery, or perhaps the whole form, what you end up with is sort of the math, right? So you end up with, maybe a potential reduction of 3 dB for a 1% reduction in efficiency. However, when you combine it with a different technology, maybe you don't get a URN reduction, but you do get a really nice efficiency boost. And so then at the end of the calculation, you have a more efficient and quieter vessel. And so that's really the space that I'm trying to have our program step into, is to start to think about that. The summary part of the workshop at IMO that really talked about beginning this at the design phase. It's potentially more challenging for retrofit, but really starting to think about these new build vessels, when you say that you are going to use an existing hull form and sort of adjust the prop, and the question is, well, are there ways to adjust the hull form, or are there ways to pair it with different things? And so, trying to start to answer those questions, which I know can be very expensive questions. And so how do you help offset some of that and get folks to start generating that information and those models? So this is an incredibly helpful presentation, and I really enjoyed it. So thank you for inviting me.
Thank you very much. You're welcome. Thank you for your comment. And indeed, some combination have been showed at the basin scale, but indeed it's worth considering it not only for the combined benefit, but also because those solutions may have different benefit at different frequencies. And that's where you need to maybe be, let's say, forced or encouraged to check different solutions with regards to their positive impact in terms of frequency band. Where you need to act on some frequency, some solution may be efficient and not on other frequency parts, and then you need to complete as well on other frequencies. Christian?
Yes, thank you. I'm Christian Krüger. I'm coming from the BSH, the German Federal Organization and Maritime Agency. And I'm coming from the field of propeller design. And I'm working on the topic of BUD and BEP guidelines for the IMO as well. And so first of all, thank you for all the interesting presentations. And one topic or problem that I meet very often is that the definitions of efficiency between the different actors are completely different. So, and I'm very, very thankful that these different definitions have been shown here. So, for example, as presented by MARIN, we have this, as I know from the propeller design as well, we have to balance URN versus efficiency, for example. Yeah, or you have, for example, different definitions for hull efficiency, or maybe for propulsion or open water efficiency, and so on. And then we have the argument with regard to EEDI and EEXI, yeah, where you define the efficiency in a totally different way. So, and when, for example, you say, okay, if you have to go slow steaming, then the propeller designer will say, okay, now the propeller is not efficient anymore, or not at its peak efficiency as it is designed for a different operational point. But for following the EEDI rules or the EEXI rules, you will get more and more efficient as you go slower, yeah, for example. And this is somehow difficult to combine if you talk to different actors. Yeah, so if you talk to the technical or design person from the propeller design or the hull design, or if you talk to the guy just like DSH that yeah, looks for EEDI and EEXI, and I was very happy to see these different definitions here, and so was as it was shown. So for the most presentations, it was shown that the energy efficiency has to be balanced with URN, and the last presentation showed exactly the opposite somehow, that you gain efficiency. And this is a problem, yeah, I don't know how to say, that we are dealing very often. And yeah, maybe you have some comments how to combine this somehow. So EEDI versus yeah, technical efficiency at the hull or at the propeller.
I have some personal comments, but before maybe some Thomas or Jan Evert, if you, or Johan, if you want to comment.
It depends a bit when you're looking at efficiency. If you are also adapting the hull form, then the hull form with a lower resistance might have a lower efficiency and still consume less fuel. So you also have to be careful when comparing. For our case, we just looked at a single vessel. We're not changing anything, so then efficiency is a proper metric, but you have to be mindful of the bottom line.
To me, you're as a very important point, and I will prevent myself from going into this debate. We have some IMO representative here. They are much more well acquainted with this discussion in decarbonization, but to me as an engineer, it makes sense to look at what happens in life and not what happens on the concept of a design. Of course, we need some things to start from at the design stage, but I would see in the future that the management of decarbonation and underwater noise is to match the real life. So more operational indexes should drive the momentum rather than one single point, EEXI or whatever single point design that we have for underwater noise. And that's the difficulty, indeed. But we have this constraint with, and it's fully understandable and agreed on the underwater noise community to come after the constraint of decarbonization. So that's what we do. We don't impair the efficiency, and we optimize as far as possible the underwater noise. That's where we are today. Combining both and having solved this difficulty I guess would come with more and more implementation of solutions and feedback from this implementation. So, Thomas, you want to complete?
Yeah, just wanted to add quickly, just to make sure that's clear, that for the air injection systems, the cost-benefit analysis was performed assuming an air lubrication system with a certain reduction in hull resistance. So that's why you see this change in benefit in terms of EEXI, which was not presented when I presented the solution itself, because that 1% performance degradation was based on what we observed during our model tests, which were not for a air lubrication system.
Thank you.
Yeah, and if I may also add something, I think especially in the past, the ship and the propeller were really seen as subsystems, and each was optimized, let's say, almost independently from each other. And that's also one of the reasons why we like to look at propeller efficiency, let's say, perhaps in isolation. But of course, in the end, it's more the rules that are important. So CEI and EEXI, so considering the ship as a whole. Unfortunately, the design tools nowadays have matured enough that we can do an optimization for both simultaneously. So optimize both the ship hull and the propeller and in interaction with each other.
Reminding that has come with the improved computation efficiency as well, and the improvement of the tools themselves as well. Not only the combination, but also the capacity of running, as you presented, hundreds of thousands of cases, which I'm not that old, but when I was younger, it was something to be done on, let's say, special sector clusters or big clusters. Now you have run it in MARIN. Anyone from the IMO floor to comment? I still see a few of you. Don't be shy, or I will kindly invite you. Marie-Lucie. Marie-Lucie is coordinating the correspondence group at IMO and represents Belgium at IMO. And your SATURN partner, you have had the opportunity to meet her when during the final event in Brussels. So just a quick conclusion from your observation of the presentation. Is it promising to have this work share? Interesting to have this work shared at IMO, Marie-Lucie. What do you think?
Thank you. Sorry. Yes, thank you very much, Eric. It was very, very interesting, quite complicated from my perspective. But yes, of course, we look forward to the workshop in November in London. I don't work on decarbonation myself, so it's complicated for me to understand exactly the link with the work ongoing at the IMO towards zero emission for 2050. But I'm sure that there are so many different ways to manage reduction of both GHG emission and underwater noise. I'm sure that we will manage to find hand in hand with the industry a way to address both issues. It was very, very interesting. Thank you very much. And also, I take it also for Belgium, because we also try to implement the guidelines, and we will have our own workshop for our Belgian stakeholders, hopefully in November, because it's important also for Belgium to tackle this issue. Thanks very much, Eric, and thank you to all the speakers today.
Yeah, the SATURN project is officially closed, but those guys are still, I guess, willing to share their very good work. Andres, Some Spanish comment or no? You cannot. Okay. I see Seftap, who is the project manager for glow noise. Do you have any specific comment? Is it some takeaways that you'd like to share at this stage with the pilot countries that are part of glow noise? Do you think it's a bit premature with regards to their stage of the stage where they are in considering underwater noise, or do you see already some shipyards in these pilot countries that would be interested in shipyards or ship owners would be interested in having this presentation shared? If you are still here, Seftap, and you can talk. You are not. Okay. May I ask then my colleagues from other classes if you have any comment from another class perspective? I see Oysten is here, and I think we have a colleague from Class NK from Japan. Don't be shy, guys.
Eric, can you hear me?
Yes, I can hear you, Seftap.
I'm so sorry. Because of this microphone issue with my computer, I'm having some problems today. Thank you very much for your kind invitation, first of all, and the great presentations. I very much agree with Marie-Lucie that I had sometimes some cognitive problems in fully understanding all the presentations. But the cost analysis, cost-benefit analysis, the last slide was quite impressive, actually, I guess, for all of us. And the interventions from the ship owners and shipping companies are quite concerning, but also reflecting the reality is that we have to think from all the perspectives. From the glow noise perspective, it's also very sad that we had the meeting with Gary as well, that the project is ending, but with very good results. So congratulations on this. But I'm trying to understand also, as you said, from the perspective of the developing countries. So as you know, in our portfolio, we have 9 countries, including 6 main, like South Africa, India. We have 2 from Latin America, Argentina and Chile, Costa Rica and Trinidad and Tobago. And all the countries' perspectives are totally different. And as you remember, we were in South Africa together, and there are some, like shipyards that would be quite interested, like Damon, but there would be more. But at the moment, the ship owners' participation to the project is relatively limited, as you can imagine, because there is no mandatory regulations. But it is what we are trying to do is to raise awareness among the stakeholders and also involve them into the process. So that is, I think, a very important step. While the science and the technology, like the feasibility studies are ongoing with the projects under the projects like SATURN and different mitigation projects. But it's also very important that I'm trying to identify during your presentations and discussions, because as we are planning the second phase of the glow noise as well, or kind of another project, which would be much more focused on the mitigation solutions, what we could bring and inform the developing countries on this perspective. So the outcomes which I guess that you will be sharing with us will be also an important input for us to design the next phase of the project with a much more focus on the mitigation solutions. Because in this phase of the project at the moment, what we're trying is to contribute to defining the baselines in the countries. unfortunately with a very short monitoring process due to the limitations in the project duration, but still it will be a good start and what we can build on it. I'm sorry I cannot give further information in, I mean, as much as detail like the other stakeholders contributing in the presentation, but it was very insightful, and thank you very much for your for this meeting and for your presentations.
You're kindly welcome. Yeah, as I introduced, the objective of SATURN is not only to show the progress on the expertise for the solution and the implementation, the assessment of this solution, but it's also to demonstrate, as it was summarized, about the maturity of these processes. The maturity, why? To justify that it's replicable. And that is the key message of the raising awareness. What has been done here has reached a level of maturity, which is replicability. It's not starting from scratch on propeller optimization, starting from scratch or on assessing what could be the dual benefit and so on such solution. There are imperfections for sure, uncertainties for sure, as usual for anything, but it's not like the old good R&D projects where we ended by saying, yeah, we need more R&D. Sure, we need more. It has been very clearly explained for instance, optimizing the vertical blades of the trochoidal propulsor, but it's details compared to the rest of the progress that has been made. And so that's the message that I think you can easily disseminate, is the availability because of the maturity. And you have these experts in the room that have done this job, not as with in their labs as a scientist with a white shirt and not communicating with the external world. Those guys are guys of on-site problems. And we have worked not enough, and it's I take my responsibility. We have not enough with the stakeholder group, but we have tried to share as much as possible, as often as possible, this result, this progress, and I will carry on my side, and I think the others as well. So yeah, this message is important for the pilot countries and for the other countries. I have noted during presentations recently that you gave recently, or that was given even by the General Secretary of IMO in UNOC. The pilot countries, it's pilot countries with the first one to test that. To embark, to engage, to see how to engage stakeholders. But any other country is likely to be more or less at the same stage. I don't criticize my country or Belgium or Canada or US, but we are a bit ahead because we have worked on other projects, but we are not that far ahead. And that's time to replicate, to have a broader impact. Positive impact. Chris, I think you had your hand raised. Sorry to keep you longer, but as far as you are interested, I'm interested.
Yeah, thanks, Eric. I was just thinking back to the first IMO workshop on the interrelationship between energy efficiency and underwater radiated noise, and the excellent study that VARD did for Transport Canada. And in particular, the big table at the back, divided up by column, reporting the percentage fuel saving and decibel reduction or change that we could expect for over 100 different energy efficiency measures. And we found that really, really useful. You know, we often quote from that at conferences and at our members' meetings. And I think it would be great if, you know, we could keep that as a live document, because some of the data in there, you know, it varies in quality. Some of it's based on estimates, some of it's based on model tests, some of it's based on sea trial results. But I think the results you presented today could perhaps slot straight into that table and be a little, improvement to it. So maybe something we could discuss at the workshop in November. Would it be possible, would it be appropriate for us to have a live version of that document that we just keep updating?
Yeah.
Thanks, Eric.
Thank you, Chris. Indeed, it's also a question and a point that we have discussed within SATURN. To me, it has to be a live document, an open document, because not only because we don't have feedback for all the solutions, but because new solutions are coming, improvement on single solutions, combination of solutions as well. And yeah, the frustration of the current experience building phase is I would say the low feedback we have on many tests and many solutions, benefits and so on. But yeah, we keep on pushing people, and it's moving, not linearly. To me it's accelerating. I don't know if it's my only if I'm only to feel this, the only one to feel this, but it's accelerating. For instance, all the wind assistance people haven't given any feedback with regards to underwater noise test so far. But some of the new projects have put in the spec to at least test this. So maybe not yet at a class notation level, but at least to test and to value that. So it's coming, and that would enhance the VARDE report that to me aims at being an open document and enriched by our SATURN work and by the project to come as well. Jerry?
Yes, I just wanted to say a few things. I guess we're probably approaching towards the end of this. Although I see some more hands, but just to address that last point from Chris, I think it's in all of our interests to see the SATURN results placed among others of a similar ilk, just to whatever is going to increase awareness and improve people's understanding of what can be done and what the implications of it are. So I certainly wouldn't have any objection to that, with the obvious proviso that we acknowledge very clearly where, what the source of the funding was and who it is that made all of these contributions, so that we don't get subsumed under VARDE, if you like. I'd like to make sure that if SATURN is placed there, that it's at least very clear that we acknowledge all of the good work and all of the contributions, the independent contributions that had gone into this. And I suppose that's also a good moment to thank you in particular and everybody else who's put the effort into doing this outside of class, if you like. The project's over and everybody took a lot of time to make this very focused, and I was delighted to see how sharp and focused it all was, and it's not easy, we know that. So just a big congratulations and thank you to you and to all of those who came and listened, and I hope benefited from the work. So that's all I wanted to say.
Thank you, Jerry. I take that the opportunity of your comment also to thank Sami from EMSA, because it has been a significant improvement in sharing what European funded projects have carried out with this intervention and submission from EMSA, emphasizing the work and detailing the work. It was not the case during the first guidelines at all. At that time, I remember going to EMSA people claiming to raise their hands for, at that time it was Silent V and the beginning of ECHO project and Sonic, and they said, we are not aware, we won't say anything. So things have changed a lot, and now the connections are made, and the work is valued, and for the benefit of all. And I feel part of the ecosystem. So it's a significant progress on it. Leila.
Hi there, can you hear me?
Yes, very well.
This is great to see all of these presentations, and I won't take away from your closing moments because I think those were good final comments. I simply wanted to say that, like many of you, I'm particularly interested in the work I'm doing now this year in support of the IMO Secretariat in this space on the role, the tangible roles to make things like what you're talking about, Chris, in terms of open source, co-editable live documentation, the ways we can really think quite tangibly about the details of some of our common interests. And I feel like people are starting to talk about the kind of edge conditions that are going to have to be worked out, and that we are talking about, many of us, in the correspondence group at the IMO, but that also are, of course, coming up in these really important projects like SATURN, which is, how, quite literally, who hosts this type of common living database? What are the components of it that can live in a space that is shared, and that can correctly note who has supported them, but can be either some format of anonymized or comparable. So there's a lot of different aspects of making things comparable, making them accessible, usable for people that are coming up in the IMO space, but that bring up other questions about whether other bodies are actually more appropriate to some of the hosting capabilities. So people continuing to think about what the resourcing that is necessary for some of our common interests to keep these results in a space where everybody knows about them and can be compared to work that's of similar ilk going on around the world, are going to be very welcome in the next few months, because I think they're definitely going to be talked about at the IMO, but they are likely to be talked about in other places as well.
Thank you, Lena. It's really encouraging and motivating for SATURN work. This was not the purpose today, but SATURN worked a lot. I think Michael is still here. Worked a lot on terminology, standardization, and that's I would say the entry filter of any standardized open source action. It's not, we all know here that it's not a bucket that we want, but a bucket where we know which fruit has been put in. So that would come at that time, but Jerry? I leave you the floor for concluding, because I don't want to spend the whole afternoon for all our guests, but I'm very pleased to have all you still here. But
I just, following on from Leila's comments there, and the really important aspect of legacy and the impact, maintaining the legacy, not alone of this, but of other projects of a similar ilk, ensuring their compatibility, their interoperability. And one of the ways that we sought to do that was through the standing up the VRE, the virtual research environment. But this may or may not be an appropriate type of platform to host the types of resources that are needed. That was conceived really to function very much in the kind of research space. So what one might find there would be data sets and code and things that you can actually test and verify and practice, and as a learning space and as a research space. I think that there's room for these different types of spaces. At a certain level, there will be a need for, maritime architects are going to go looking for tools and for code to try out new things and these new codes that have been developed. So yes, and new methods and new workflows, all of those things. So it's the level of detail that we can capture. You know, today I think was a perfect example of how you can synthesize things and present them really effectively in a short time. And I hand it to you for having done that. But I guess we need to consider all of these different end-use requirements and their interoperability and and their sort of maintenance over time. So it's that curation piece is key. It really is, and it's the case with so many different initiatives, not just this one.
Thank you, Jerry. So if there is anyone ask with a question, please raise your hand. Otherwise, I really, really sincerely thank you, Jerry, first for coordinating this great project. Johan, for this tremendous work and your really nice coordination and your invitation to me regularly, and you all for your commitment in delivering your excellent work, and you all, the SATURN stakeholders. SATURN adventure is ending, but the URN is ongoing. So I hope we'll meet soon again, and keep safe. Bye-bye. Yeah. And I will send the slides.
Bye-bye.
Yeah. Thank you very much,
everyone.
Bye.
Thank you. Thank you very much.
Bye.
Bye, everyone. Thanks, Eric.
Cool. Thanks, Eric.